Today. My name is Michael Gora. I am a senior product manager, which I guess means I'm old, for AMETEK Process Instruments, with responsibilities covering the photometric analyzers that AMETEK Process Instruments has in its suite of solutions. Along with me is Jochen Geiger. He is
Okay.
Oh, you want to introduce yourself, Jochen?
Yeah. If you call yourself because senior because of your age, then I should call myself senior. I'm with these sulfur products for more than 30 years now. I started my career in the process industry 79. So I have some years carrying on my shoulders, and I'm happy to present that with Michael today. My responsibility is sales and service in 1/3 of the world, Europe, Africa, Middle East, India, but I'm happy to help wherever you ask me to get involved. So if there is questions, we ask them during the presentation. We'll try to be on time and have a chance to answer all the questions which are coming at the end of the presentation. Back to you, Michael.
Okay, thank you, Jochen. So I am going to try and get us going here. All right, so what we're going to be discussing today are some of the common emissions and operational issues that might be observed when working with a sulfur recovery unit, or as we'll refer to it as in the rest of this presentation, an SRU. What may be causing those issues, how to identify, confirm, even prevent the causes of those issues, and then some potential solutions that AMETEK has available. A quick reminder, SRUs really have one primary purpose, and that is to remove sulfur components that are coming into the sulfur recovery unit from either some other part of a refinery or a gas processing plant, in some cases, other petrochemical facilities, steel mills. Again, what we're trying to do is get rid of the sulfur that's coming into the sulfur recovery unit before it goes out the back end of the sulfur recovery unit. And the reason for that is what industry does not want to do is they do not want to send sulfur dioxide and hydrogen sulfide, SO2 and H2S, into the atmosphere or out into the environment. And the sulfur recovery unit does a wonderful job of capturing quite a bit of that sulfur that comes into it. When it's operating properly, you can, as the bullet point number 2 here states, for every ton of sulfur recovered, eliminates 2 tons of SO2 going out into the atmosphere. This has been driven largely by regulations and other environmental concerns, but it's really come a long way, and that's what we're going to be talking about today. Is kind of going beyond where everything started, and new components have been added to SRUs, and that's provided some additional opportunities for analytical equipment to come in and help optimize that capture and recovery of the sulfur in the feedstock. And then final bullet point on here is something to remember as well, is that although traditionally you don't look at an SRU and say it's a money-making venture, what you do hope ultimately is that you can break even, because that captured sulfur can be sold and reused for other industries such as agriculture, fertilizer production. It can be used in medical applications and some other industrial applications. So there is some financial benefit to capturing that sulfur, in addition to preventing any environmental concerns. So hopefully everybody can see my screen. If not, John, if I do lock up, just one quick note. Do me a favor, send me a quick text, and I'll try to pause and get back online here. A typical SRU, what we're looking at here, just as a reminder, is on the front end, you have some type of furnace assembly that goes into the condensers and converters. Ultimately, this is where a vast majority, this is going to be 98, 99%, hopefully, of the sulfur is captured. And it's either, the legacy term is sulfur pit, but it's effectively a sulfur storage area. And then what we've seen more recently is tail gas treatment units have been added. And what they do is they help remove some of that additional sulfur that might have been still coming out the back end of the CLAUS unit here, and treating that before it goes out through the stack here. And that's where we're going to spend a good portion of our discussion, is on the tail gas treatment unit here, identifying some issues that can be, I guess, located or it can be addressed here. And we're also going to be talking on the front end here, the feed portion of the SRU. So starting with the feed gas, it typically consists of hydrogen sulfide, very large percentage, and you can see that down here, up to 100%. CO2 is typically very high, more so when we're talking about natural gas processing. Refineries, that number could be considerably lower. And same thing, well, I guess inversely, what you see is the opposite, is ammonia can be much higher in a refinery than it would be in a gas processing plant. And again, that has a lot to do with the feedstock that's coming in. Getting back to that, sour water stripper gas is one term that's frequently used to identify the feed gas. Another one is acid gas, or quite simply, and probably the most appropriate term, is the CLAUS inlet. So those are a couple different terms you may hear thrown around. And again, the key components that will be analyzed are hydrogen sulfide here. We're going to talk a lot about this right here today, total hydrocarbons that may come into the mix, but we'll also touch on the importance of looking at ammonia as well. And again, that'll be something that Jochen talks about here in a little bit. I mentioned it earlier that the goal is to recover, 98, 99% of the sulfur. This is largely driven based on where the plant is located. And what I mean by that is where it's geographically located. There are different regulations. In some locations, you don't need to be 98%. You might be 90%. But as a general rule, 98+% is the target. And most plants are trying to recover from the sulfur that comes in. And again, there are some locations where it's extremely difficult, and that's the benefit of having that tail gas unit put at the back end of the CLAUS unit, is to make sure you're achieving 98, 99% of the sulfur recovery. In order to do that, you need to properly manage your heat at the reactor furnaces. And I'm going to skip ahead to the next slide so I can kind of point this out. Is that you need to make sure that you're properly managing your heat here. You want to manage your flow coming in here. You want to manage the air mixture that's coming in. Again, the feed is basically your fuel, if you will, and the air is required for the burn in the furnace here. And then what we want to do is make sure that we're properly flowing through here. This is a condenser, and then this is a converter. There can be two condensers. There can be two converters, there can be four converters. This can vary pretty widely depending on how much recovery is expected. Again, largely driven by regulations of where you're at or company goals. The other thing that you need to manage is your catalyst here. Make sure that that's healthy and operating as it's supposed to. And ultimately, this is what it all comes down to. It's a fairly simple chemical equation that's shown here. Is we're starting out with high levels of hydrogen sulfide. We're mixing in that oxygen, and I mentioned that here. It can be pure oxygen. Some plants do that. Others just use instrument air and introduce that here. And then and this will be the burn part here, will result in these products here. But these are the ones that are of real interest as we then go into the catalytic reactions. Again, those are taking place here in the converters. That will give us our sulfur at the end here, which kind of looks like this. And it's fairly common to walk through a sulfur recovery unit and see little patches of sulfur like this sitting on the ground. So again, that shouldn't really surprise anybody, but ultimately what we're trying to do is catch tons of this in the storage pits or the sulfur storage areas. One quick point, I think I kind of glossed over this. This is a very high temperature reaction that's giving us these components here. And what's actually happening in the condensers here is we then drop the temperature, or the temperature is dropped here, and that allows that sulfur to fall out, and the gas continues on. And this is a little bit higher temperature. This converter right here runs a little bit hotter than this one here. But these condensers right here typically stay pretty consistent in terms of temperature, trying to get that sulfur to come out. And then final point on this slide here is I just want to point out something that we'll refer to. This is where you would typically see a tail gas or air demand analyzer. And this is controlling about 10% of the air mix that's coming into the reactor furnace up here. We're not going to spend a lot of time on this. I think this has been presented for decades, kind of what's going on here. And every SRU has a tail gas analyzer, or at least a vast majority of them have a tail gas analyzer in place already. So with mostly what Jochen and I are going to talk about today are those situations that arise and can be identified, hopefully prevented, by making a measurement somewhere other than at the tail gas analyzer. And final point is we're calling this a tail gas analyzer. Again, it can also be called an air demand analyzer. Don't confuse that with the tail gas treatment unit. Analyzers in there are different analyzers making different measurements. So when we talk about a tail gas analyzer, we're typically talking right here at the end of the CLAUS unit. So let's talk about the first issue, and this is a fairly common one, one that does get brought up, and it usually leads to some concerns being raised internally at a refinery or gas processing facility, and that's the sulfur dioxide emissions are exceeding the expected limits. That's what we need to remember. Those of us on the call are typically trying to either mitigate those issues or resolve and correct them, is that SO2 emission going up at the stack is typically not the cause. I mean, that's the symptom. That's what we're seeing as a visible effect of something else going wrong. So what we need to do as troubleshooters and engineers, solution experts, is we need to go in there and try and figure out, well, why is the SO2 concentration going up at the stack? And why is the environmental individual getting phone calls saying, hey, we've got a problem here, our levels are going high? Why is the plant manager being told, hey, what's going on over with those at the stack in the SRU unit? So the red flag is up, and now you're trying to troubleshoot and figure out, well, what's going on here? There's a couple things to consider. And again, that's what we're hoping to get across today in this presentation, is that it's not necessarily just one item, but it doesn't hurt to have some equipment in place that allows you to check and see if these different stages in the sulfur recovery unit are causing that SO2 emissions exceedance. So one of the first one that we'll be discussing is improper air or oxygen to fuel ratio at the primary reaction furnace. What are some ways that we can look at that and understand, are we introducing a proper amount of oxygen up there, or air? Another is loss of hydrogen in the tail gas treatment unit. And that, again, it's usually not that hydrogen isn't being provided. It's more often the hydrogen is being used up. And we'll get into more of that, and how to identify that. Or the third common one is the amine, or the absorbing component in the tail gas treatment unit, is either spent or it's deactivated. Something's gone wrong and it's not pulling out what it's supposed to be pulling out in the tail gas treatment unit. So the first one that we'll talk about is the incorrect air to fuel ratio. If this is the case, what you will not see is the expected conversion of about 60% of the incoming sulfur components to being converted over to elemental sulfur. Where that would typically manifest itself is at the tail gas analyzer. You'll see some higher levels of H2S and SO2. But how do you know that, is it a problem in here, or is it potentially something that's being caused at the feed gas at the inlet? We're not getting what we expect to be getting. And that's what one of the first things that we'll need to look at is, why is that H2S not being converted or reacting properly with the oxygen that's available? And one of the potential items that may be the issue is if hydrocarbons are suddenly increasing, then what you will not have is that oxygen available to react with the H2S and convert over to this right here, this SO2 here, because those hydrocarbons like to consume the oxygen at a higher rate than the H2S, and they do fairly easily. So what you end up with is a negative impact on your conversion efficiency. And what you will frequently hear, and again, Joken's going to really get into this in the next couple of slides as I hand it over to him. But where the biggest issue that most plant operators and engineers talk about is when those hydrocarbons suddenly go away. So you saw that the hydrocarbons were elevated, you added more oxygen to account for them, and all of a sudden they disappear. Well, now you're going to have too much oxygen in there, and that's going to react very aggressively with the H2S at the inlet, and you're going to generate too much SO2. And that's a real problem downstream, especially in the tail gas treatment unit, where the amine doesn't want to see a bunch of SO2. So again, I'm going to hand this over to Joken, and he's going to talk a little bit more about the issue and how to resolve it. Joken?
Yep. Okay, let's go for the next slide now.
Are you able to do so, or do you want me to click for you?
I thought I would be able to do so. It should be, but okay. It's low. So I think better let's go for it. So what this slide is showing is an increase of the hydrocarbon in the feed gas. And before I go there, let me make some comments. And I will go back to the previous slide. We list the different hydrocarbons just to demonstrate how much more oxygen higher hydrocarbons take than H2S. But the question here is not to know how much C1, C2, C3 I'm getting to it. The question here is, do I get hydrocarbons? Do I get them fast? Do I get a lot? It's not the question of separating them. We always have to ask the question, it's nice to measure something, and we easily are getting very excited when we see, we can do that, we can do this. But we also have to ask the question, what makes sense to measure? I can do a lot of things, but I always say, do I need a Rolls-Royce to go to the corner shop and buy my daily bread? I don't need. A bicycle or a small Volkswagen will do it. And the same question we have to ask here. What is possible to measure and what makes sense to measure? And when we ask that question, we also have to see the point, what can we do with the signals we are getting from a measurement? So what are the possibilities we are getting? What is how much can we influence the control? And therefore that slide, which is a courtesy of Comprimo from a real installation, it's very nice. So we have two factors here to see. We have the air demand signal coming from the air demand analyzer. And as Michael just said correctly, that's controlling approximately, as a rule of thumb, that's controlling 10% of the airflow to the reaction furnace. And during normal operation, that's more than enough, that's more than sufficient. And most operators don't like to vary too much on the control, because there is possible scenario that you can control too much, that you get too much swing into the unit, and that you lose control by reacting too fast. But what, again, coming here, we see that increase of hydrocarbons, and we see that the calculated acid gas to air ratio which is the acid gas to air ratio going to the reaction furnace, suddenly increase. And we also see on the red line how much longer it takes for the air demand analyzer to give a control signal. And that's not because the air demand analyzer is slow. It's because there is a process to overcome. There is a large process which a lot of surface with a lot of volume to be changed over the time. And only then the air demand analyzer can see the reaction and give a feedback signal. And that might be insufficient in case of a real hydrocarbon breakthrough. And we have to see here two scenarios. One scenario is the classic one. I have an SIU, I have a 3 or 4 stage CLAUS unit, and I don't have any tail gas cleanup unit. Then I'm very much worried when the hydrocarbons are coming because I want to react fast. I don't want to lose any efficiency. I want to be always at the optimum point of control. And then we have the scenario, which is mentioned by Michael. We have a tail gas cleanup unit, and it's now more common and globally common that these tail gas cleanup units are amine-based cleanup units, and we will discuss them in detail. But here the worry is not high H2S. The worry here is high SO2. So when we are looking now on the right side of that slide, we see that the hydrocarbons are disappearing as fast as they are appearing. And again, if you don't measure the hydrocarbons, you don't know it. And it takes even a little longer for the air demand, and that has to do with the chemistry. It has nothing to do with the analyzer. It has to do with the chemistry of the process until the analyzer gives a feedback signal. But what's happening here? Your control system has adjusted the airflow to the reaction furnace, so it has given more and more air, giving more and more oxygen, and then suddenly the hydrocarbons disappear. Boom, they are gone. What happens? The SO2 shoots up, and that's shown here in that curve. The H2S goes down. That means when H2S goes down, SO2 goes up. And there is scenario likely which can cause a deficiency of hydrogen in the tail gas cleanup unit. And we will go into that in a couple of slides. So let me go to the next slide. It always takes a little bit when I do it from here. Michael, I think you should do it because it's too much. It reacts slowly if I do it. Okay. So there is a solution to it, and I have been long enough in industry that I have gone through generations of discussion of that point. So many technologies has been tested, thought about, but nothing was really considered as a practicable solution. Again, we have to go back. What can we achieve? First, analytical wise, but second, also control wise. Of course, I can separate all the hydrocarbons and give them as a discrete signal, and I know exactly how much methane, how much propane will come. But what do I do with it? If I go that way, it will take 3, 4, 5 minutes analytical time to analyze it. What happens in that time? I will have my answer already from my air demand analyzer. So any analysis you do about the total hydrocarbons to be used in a control has to be faster than the signal comes from your air demand analyzer. To do it practically faster, you have to go for a measurement, a simple measurement of total hydrocarbon. And simple here is really the key word. I've seen in my life a lot of instrumentation people who say, Mr. Geiger, you are a nice guy, I like you, I respect you, but this measurement, I really don't want to go for it. It's very toxic. You know how much H2S we have? I say, of course I know how much H2S we have. And I know it's toxic. So that's why AMETEK, that's why we have thought about a solution. And that's not only an analyzer solution, it's a total solution. It's an analyzer with a probe. And on that probe, this probe is only made for this application. It's a heated acid gas probe. It has a dual shut-off module where we can isolate the instrument safely from the process. It has no moving parts. I always say in my presentation, if anybody comes and tell you, it's a simple H2S measurement, of course I can do total hydrocarbons. How do you want to? I use a pump. I say, okay, go away. A pump, in my word, in my view, a pump, it's not a question if it fails. It's only the question when it fails. Every pump will fail. Every pump will have a leak sooner or later. In most cases, it will have the leak sooner. What happens with a leak if you have 90+% H2S in the gas? You have 5 seconds. That's it. So we have to see two things here. It has to be a practical solution. It has to be as practical that we can use the signal for control. That means the measurement has to be fast, within seconds. We don't have the time to make a detailed analysis. We need something to react. If somebody is interested in the detail, he can have a secondary measurement. I've seen that, to analyze really the root cause where the upset is coming from. But that's not the question here, what we want to discuss today. We want to give a fast signal to react to process changes in a fast time to protect other process equipment and to provide the best efficiency from the process unit possible. And therefore, we have that solution, which is analyzer and probe, and that's one solution. And I say, keep it simple. Keep it simple. Simple means safe. Okay, next slide, Michael. We have discussed that for TGTU, and we will go more into detail for that. But also, I want to mention there is a lot of SIUs which do not have these amine-based TGTUs, which have other tail gas cleanup units like sulfurin, like super CLAUS, like EuroCLAUS. There's even 4-stage, just modified CLAUS units. So there is all different scenario. What I have experienced in my years in the industry is we may train our operators, but rarely we train the maintenance teams. We have rarely seen end users training the maintenance teams on the process. And that's the part where is offered by AMETEK. You can only improve your process performance if you have the right equipment and if you have well-trained people working in this process. And that's not only the operator side, it's the operator side and the maintenance side and the instrumentation side. And I have done it multiple times with customers. And I insist, if we do this kind of training, understanding upset conditions, understanding the meaning of the instrument, it's so beneficial if we do it with operators and maintenance teams together. Okay, I need to keep a look on the eye, Michael. Let's go for the next slide. So when we look into the possible sample points, we have spoken so far about the feed gas, and we do the feed gas in the acid gas and in the sour water stripper gas. The sour water stripper gas requires the measurement of ammonia. The ammonia is an unpredictable thing, like the hydrocarbons, and it has to be known to the process operators to make preventive actions in case the ammonia is spiking up or going down in an unpredicted way. And I tell you, the unpredicted is more often than we would like to have the unpredicted. One point which we have not touched is the sulfur pit analyzer. So if there is any interest, we can have a separate session for that, as this is a pure safety measurement. Now we will concentrate on the tail gas treatment unit. So you see we have multiple points, and we will concentrate on the quench and the absorber stripper. That's the 2 points we would like to discuss today. Okay, go for the next slide, please, Michael. So what is the duty of an amine-based tail gas treatment unit? In very simple words, it has to convert all sulfur components into H2S. And as we see here in the flow sheet, this conversion is happening on a cobalt molybdene catalyst. Then we have a quench tower where we quench the gas to bring the temperature down. Then we have the absorber and the regenerator. We'll go step by step through this process. Bottom line is the recovered H2S is being sent back to the front end of the modified CLAUS unit. So sent back to the reaction furnace. When we look, I'm not a chemist, but it's somehow important that we understand a little bit of the chemistry which is happening here. So we have multiple sulfur components. We have the SO2, which is the highest portion, but we also have elemental sulfur. We have sulfur dust. We have sulfur in vapor form. We may get some sulfur fog carried over. We get also the other sulfur components, COS and CS2. All of them have to get converted into H2S. So what do we need to do this conversion is clearly we need hydrogen. Hydrogen is a must, and hydrogen can be a troublemaker. What is shown here, you find scenario where the hydrogen is entered as a reducing gas from the hydrogen unit. You can find scenarios where you have an inline reduction burner, that you crack some natural gas, that you crack the hydrogen off, that you get the hydrogen from that. But I also spoke to some operator, and that's a big headache, who only get the hydrogen as a byproduct from the reaction furnace. Of course, they have some more headache operating the TGTU. What is clear here, we have to convert all sulfur components to hydrogen. Also clear, as long as we have excess hydrogen, we don't have any other sulfur components. That's a good thing. That makes a lot of things easier. But it's not that easy. We should not get any SO2 breakthrough, as SO2 is a poison to the amine. And we will discuss that in the next slide. I just want to show you in the next slide a nice example of how that can look like. So here you look on the blue line and look on the green line. That demonstrates on a live picture how it can look like and how it happens. The SO2 from the modified CLAUS goes up, the hydrogen goes down, and you see how easy it can happen that the hydrogen is going into the negative, or that there is no excess hydrogen. So it's not theoretical talks. It happens really. If you go to your operational room, you can see it. An average concentration value of the hydrogen is 3 to 4%. That's what people try to maintain, that they have enough room to get a buffer to the worst case scenario. Okay, take the next slide, Michael, and I will come to that. I've spoken to many operators in my life, and most say, you know what? It's not easy and not nice if I lose the air demand analyzer. But if I have a TGTU, I'm well trained, I can operate for some time, I can operate the unit without the air demand analyzer. But to be honest, I don't want to operate my TGTU, my tail gas treatment unit, without the hydrogen analyzer. I say I wholeheartedly agree with you, because things you do wrong in the modified CLAUS, you can make it up in the TGTU. That's a nice thing of the TGTU. That's what you pay all that big money for, to get that nice unit, because it's providing a high efficiency. It's providing a good efficiency margin, but somehow it's also a little bit complex to operate it. If everything runs well, it's very smooth. But I'm asking then the question, see, if something is so important for you, what do you do if some stuff is important? You have it redundant, right? I typically bring the example, if you fly across the Atlantic, would you ever sit in a plane with just one engine? Even when people say, I have the best engine on the globe, would you like to sit in that? No, you want two engines, well knowing that the plane can fly with one. Why do we make that difference here? I have seen rarely, some it's coming more and more. Some plants I see where they say, yeah, these people are absolutely right. The hydrogen is so important for my operation, I should have it redundant. And I say, you should have it redundant because you can get it almost free of charge. Almost free of charge, not fully. What people typically tend not to recognize is everybody is looking on the analyzer price. But are we looking on the right thing when we look on the analyzer price only? No, we have to look on the total installation cost. As a good example, the total installation cost includes civil engineering. You need that platform, you need the utility supply, you need. At the end, if you make the calculation correctly, you will come up that the instrument only is maybe 30% of your total installation cost. So when you add a little extra component here, which you get for a little incremental, then compare it with the total installation cost, and you will see you will get it almost free of charge. So what are the points of interest here? Is hydrogen at the quench column outlet. That's a very classic hydrogen measurement point in a TGTU. It has moved a little bit to the absorber stripper column outlet, where we measure the H2S as a quality measurement to prove that the unit stays within the limit, to make sure that you get what you want out of that unit. But there is a redundancy issue, and maybe you take the next slide, Michael. What we see here, what are the interesting points to consider? And also that's a little looking into the future. So classic, we have hydrogen at quench outlet, H2S at absorber outlet. So what else can we do? What else can be beneficial? On the absorber outlet, beside the H2S, a lot of people want to see the COS, and I think Michael has a couple of example for you. The COS will give you a good idea about the catalyst, about the cobalt molybdenum catalyst. We have done with some customer also CS2 measurement. That's also telling about the condition of the catalyst. And we can do the hydrogen measurement at that point to have the hydrogen redundant. The absorber will not change the hydrogen concentration. So it's the same. If you measure absorber outlet or quench outlet, it's the same hydrogen concentration. But what is the benefit if we go quench outlet? What can we do there? At the quench outlet, we should ask the question, should we not measure the H2S at the quench outlet as well? You may ask, why should I do that? Point is, how do we know when the absorber H2S goes up or down? How do we know what is the cause of that? For example, you see a steady increase of the H2S at the absorber outlet. So what do? What can you do without knowing how much H2S goes in? What can be the causes? It can be that the amine is getting deactivated. It can also be that your regenerator is less effective, that you have too low temperature, that you're operating on too low pressure. But it also can be that you get more sulfur components from the modified CLAUS unit, that you get simple more, and that you have to increase the circulation rate of your absorber. And that's an interesting aspect which I've seen in deep discussion at several platforms, at several forums. We not only have to ask the question of the SO2 emission, we also have to ask the question of the CO2 emission. And as much more we take on load on the regeneration, as much more we emit CO2, which is a question of tomorrow. So we have to find the right balance between H2S and CO2. Why to emphasize on the H2S and therefore get high on the CO2? Maybe we stay on the normal on the H2S and get a little lower on the CO2 emission. So it can, an inlet-outlet measurement gives a 24/7 performance measurement on the absorber. So for a summary, I give it back to Michael.
Okay, thanks, Jochen. So yeah, just kind of touching on, I think a point that Jochen's made here pretty consistently is monitoring the hydrogen and the hydrogen sulfide both. Oops, how about I put the arrow back on the screen here? Before and after the absorber has benefits that are not just indicative of whether or not you'll have SO2 coming out through your stack here, but also could also point out, how much hydrogen sulfide is going out here, and what else may need to be taking place in terms of maintenance on the absorber, whether that's amine or some other type of absorber that's there. The problem that we need to remember is that if H2S is elevated and going to the thermal oxidizer here, it's not going to go out as H2S, which also is a bad thing, frankly, but it's going to get converted to SO2. And that gets us back to the point that we started at. Our SO2 levels are elevated at the emission stack. What could be causing that? And if you don't have visibility to what's coming out here at AT6 after the absorber, you may miss an opportunity to diagnose it. You may, as Jochen I think was referring to here, you may replace your absorber when you don't need to. You may think, well, it must be excess H2S coming over here. Without measuring, you just don't know. So the other point that we didn't make, I don't think we sat on too long, but anybody that's an end user on this phone call is well aware of, is amine is very expensive. You do a couple of amine dumps or replacements in a year that aren't required. They've paid for these analyzers, right, Jochen?
They pay for many analyzers.
Yeah, exactly.
So some figures, so a liter of amine costs between $30 and $60 per liter.
And how many liters would be in a typical absorber?
A couple of cubic meters. A lot.
Yeah.
More than you ever can spend for another. I think as a consequence, we have to increase our prices. No. If I look into that.
No. Thanks for throwing me off my groove here. So the other point that Jochen made a couple times was if you're going to recognize that there's value in making the measurement both before and after the absorber of H2S, then why not include hydrogen both on the front and the back end of that as well? Why? Because it really doesn't cost much to add it to an analyzer. We can incorporate that in our 931 or our 932 analyzers. And if you did have an issue with the measurement, let's say right after the quench column, you start getting a hydrogen reading that seems very low, but you're not seeing that at the second analyzer point after the absorber here, and all your other readings have stayed pretty consistent, then it's a nice diagnostic tool. You know that there's obviously an issue with your hydrogen thermal conductivity detector sitting over here in AT5. Again, it's an insurance policy. And nobody likes to overpay for insurance, but at the same time, nobody wants to be spending hundreds of thousands of dollars replacing absorber needlessly. So throwing in an extra measurement point here on an analyzer, it's really insignificant in the grand scheme of the analyzer system and solution. So again, we're getting a little short on time. We're trying to do this in 45 minutes, and we're just a hair beyond that. But what's nice though is that we're hitting a point in this overview that is kind of redundant a little bit, because what we were specifically talking about previously was, how do I manage SO2 excursions? How do I minimize them? How do I find them? How do I identify that where they're coming from? The next thing that we were going to talk about was specifically the loss of amine efficiency. Is there something going wrong with the amine? Because if it is, it's not pulling H2S out, and I'll point out where that's at down here. This H2S is being pulled out here in this amine here, and if the amine is not operating correctly, or as Jochen said, if the flow rate is incorrectly set here, you could see higher levels of H2S coming out, and then that obviously gets converted to SO2 at the thermal oxidizer, and hence you get the elevated levels of SO2. We've already talked about the expense, so I don't need to talk about that anymore. But what we didn't talk about, and again, I think Jochen started to go down this path, and I have too a couple different times, is typically that amine is being regenerated and that H2S is being pulled out of the amine over here, and then that's being sent on back to the front end of the entire modified CLAUS process. Okay, so that's a good thing, but there's energy associated with that, and if you need to be running this hotter, or if you're running it more frequently, that's an energy cost that you're incurring that you really probably don't want to be incurring to try and get that H2S out of the regenerated, or the prior to being regenerated amine or absorber. So that's another point to keep in mind, is you don't want to be doing unnecessary regenerations, or doing them more frequently than you have to, is probably the best way to say it. So another solution from AMETEK is, again, our 931 or 932 analyzers. They include a UV bench as well as a thermal conductivity detector. And that and what needs to be kept in mind is that hydrogen's a tricky little bugger. It doesn't you can't see it with UV. You can see it with TDL, but it's not a very good absorber. So that's a less than ideal solution. You really can't do it very much with traditional IR. So what you end up with is a thermal conductivity detector here. Is included in a 931 or 932 analyzer, and then the H2S is viewed via the ultraviolet in there. So those of you that have been following along and paying attention, you've probably picked up, wait a minute, you're basically saying you're going to measure you're saying the solution to better amine management is to put an analyzer at AT5, AT6 from that prior slide. Let me pop back here, put one here and here. Well, didn't you already tell me that? Didn't Jochen just say that I should have those in there? Yeah, he did. So basically what we're talking about is getting better visibility on your amine management, in addition to identifying whether or not the amine itself is truly spent and resulting in higher H2S concentrations, making it to the thermal oxidizer and then going out the stack. The other point that we briefly touched on was that you can add carbonyl sulfide at this point, and that measurement of carbonyl sulfide, and let me just show you again what we're talking about here is if you had carbonyl sulfide measurement right here, if you start seeing that level go up, it's a pretty good indicator that your catalyst at towards the front end, it might help if I was pointing to the right slide, it might help you identify whether this catalyst is going bad. Again, it's not, you typically wouldn't just suddenly see COS spiking. So that might be a good indicator that this is spent if your COS levels start to go up here. And again, that can be added to an analyzer solution that you've already added to maintain or monitor your amine solution.
For the completion, CS2 is also possible.
You're correct, correct. And that might be for those that are trying to do a mass balance equation or something like that.
Yeah.
It might be good to measure CS2 at this point as well. So a couple quick slides here to kind of wrap us up. I just wanted to show an operational one here. Again, we've been talking about the back end of the tail gas treatment unit. This is what it would normally look like. A couple 10, 15 ppm H2S would be seen here. COS levels typically really about the same amount. Keep in mind there's a difference in scale here, but you're looking at the low ppm levels of COS here. And what you don't want to see as normal operation is see numbers like this. You don't want to see graphs where everything's spiking. And in this case, your COS is suddenly spiked. And then after some type of resolution, then you see the H2S level is spiked. There's no point in getting into exactly what we're seeing here and trying to diagnose anything. The important takeaway with this image here is that you would see it. If you have an analyzer that's sitting at the back end of your tail gas treatment unit that's measuring H2S and COS, you would see these spikes, and that would give you an indicator that something's gone wrong. And then you start thinking about, well, why am I having a spike in COS? And it gives you an idea of where to go look to solve your problem instead of blindly replacing parts left and right. Jochen made an example, I'm sorry, Jochen, were you going to say something?
No, go ahead.
Okay. Jochen made an earlier example about taking the right car to the corner lot, not taking a Rolls Royce. I would say it's the same thing if you've ever done any car maintenance, and you've got something going wrong and you just start swapping out parts, that can get pretty expensive. And it can also get very timely. So if you had a little bit more visibility and you could put it up on a rack and really look at, what's causing that rattle or that noise without just swapping out parts randomly on your car, you would do it. It's the same thing here in your tail gas treatment unit and your SRU in general. So
one closing comment for me on that is, and that's to the users on that call. If you look on a licensor spec sheet on the tech sheet, what these people do is cut and paste. They do the actual one like they did the previous one, but the previous one was already done like the previous one. So on that sheets, you are a couple of generations behind. And as I said before, look into the application, look into the needs, understand what is possible, understand what is the price impact, and that's highly important to understand that. But don't believe the technology which was available 10 years ago is a technology which is available right now. So we can do more things right now at a reasonable cost factor. And as Michael showed in that slide, it's not that the readings is always constant. That would be too nice. The unexpected is more often happening than it's expected. Okay, that's for me.
Okay, thanks, Jochen. So just to kind of wrap us up here, again, we've gone through a couple different conditions that can occur or issues that might be occurring, specifically SO2 increases at the stack or frequent amine replacement that are real issues that do pop up in sulfur recovery unit operations, and throwing in some analytical solutions that can confirm operating conditions are going well. Or identify issues that may be causing what you're seeing go out the stack, the elevated SO2 levels, or in some cases even maybe H2S levels going out. But they can also help locate exactly where that problem's coming from. So it's not just giving you a heads up that something may or manifest itself or may become an issue from a regulatory standpoint. It can actually help you figure out why you're not operating like you normally do, or why you're having those regulatory issues. At a minimum, our recommendation is to include some type of measurement at the front end, feed gas analysis. Again, to Jochen's point, if we just go by what was historically done, this can get overlooked. The reality is that technology changes, and analyzer capability changed, and we do now have the ability to make that analysis on the front end, and it gives you better insight to your process. Why not take advantage of it, operate better, operate more environmentally friendly, whatever the case, more financially efficiently, whatever the case may be. Measure the hydrogen in the TGTU. That is absolutely critical. At some point, it doesn't matter whether it's before or after, just make sure you're measuring the hydrogen and do it redundant if you can. It'll pay for itself, trust us. H2S before and after the scrubber can help give you much better insights on what's going on with your amine, and again, help drive some operational efficiencies, some cost savings, as well as reduce environmental issues. And then Jochen and I cannot possibly do a presentation on a sulfur recovery unit without mentioning, of course, you still need an air demand analyzer or a tail gas analyzer. And that's what I'm showing here is the Model 900, and which does remote sampling and does the analysis, or the 888, which is shown down here, which actually gets mounted right on the pipes. No heated sample lines required. I guess in wrapping it up, we will do the usual. We'll direct you to our website, www.ametekpi.com. If you have additional questions, ametekpi.com has a spot up there where it says contact us. Please feel free to fill in your contact information and reach out to us. Indicate that you watched the presentation, and if you have specific questions, there's a spot available on there for you to indicate that you would like to get more information from either Jochen, who spoke, or myself, Michael. So again, I guess at this point, I'll open it up to any questions, Sean, that have come in.
There was none in the chat, Michael, but I did get one or two emailed here to me. One question goes back to something earlier on when Jochen started his session and talking about the reaction of the air demand analyzer. And the question was around what's the typical lag time or delay time between when you see the hydrocarbon spike or decrease go away and when you might get a reaction or reading from the air demand analyzer, and then ultimately what's the impact on the process when that if you have that lag.
Good question, John. I should have mentioned it. Typical lag time of process is between 90 and 270 seconds. It depends on the throughput. It depends on the size of the process unit. Very clear. When you see the H2S going up, the process impact is you increase the oxygen flow to the reaction furnace because it's telling me I don't have enough oxygen to react in the reaction furnace to give me the ratio of H2S to SO2. That's the short answer to it.
Okay, thanks, Jochen. And then, Michael, the other one was there's obviously a lot to the SRU unit that can't all be covered in an hour. So if folks are interested in talking to somebody directly or learning a little bit more about SRU, I did put the link into the session that you guys will do at the Sulfur Recovery. I'm sorry, at SulphurCon 2021. But just curious, Michael, where folks can get more information or talk to somebody if they want to learn a bit more about other measurements in SRUs.
Yeah, no problem, John. So as I mentioned, AMETEKPI.com, and I'll scroll back to that. It's just www.ametekpi, and we have a contact us button located there. So you can start there. The other one is most people on this call already know who their AMETEK contacts are. Frequently, that's a representative firm or a distributor. Feel free to reach out to those extensions of AMETEK. They're experts on sulfur recovery units, and in most cases, and if they get hung up or stuck on something, they know where to contact Jochen and I. So yeah. I think those are a couple different routes, John.
Okay, and then there was a question in the chat that came in on what kind of levels are produced on hydrogen coming from the reaction furnace for the TGTU.
Hydrogen is a byproduct which happens in the reaction furnace of the modified CLAUS unit. Its concentrations between 1% and 3%. It's on the edge where a TGTU can operate with. In most cases, as the next, you have an RGG, you have an inline burner. But before we go into that detailed discussion, there might be people on that call who say, okay, that's interesting. Can you do a separate one for me? Michael and I, we are very happy, depends on the location. We are very happy, and we can go more in detail when we do it in an individual. And when you ask us for that, we are more than happy to provide that kind of discussions. And then we go more into your specific details, because then we will ask you, what is your process setup? What do you have? What are the issues you have? In our previous lives, we have been traveling around the globe for that. Now we do it in online courses. So, but reach out to us if you want to have an individual one. We are very happy to provide it to you on an individual basis.
Okay,
Great
great.
point.
Thanks,
Yep.
Jochen. And thanks. I know we're about a minute or two over time, so I do want to thank Jochen and Michael for the session today, and also obviously thank everyone who attended today's session. Hope the content was informative for everybody. I did post several useful links on the products and how to get in touch with local contacts related to today's presentation in the chat window. And as I mentioned at the beginning, the session, the recorded session will be posted on the AMETEK YouTube page within the next 24 hours or so. So thank you again, everyone, for your time, and enjoy the rest of your day. Thank you.
Okay, bye.